Okay, we're going to talk about diabetes, glucose regulation, and hormone regulation for the next two presentations. So this is our first portion. This is glucose regulation 1. Glucose regulation 2 will be performing on Zoom next Thursday. So we're going to start out with really understanding hormones. If you don't understand hormones and how they work, how they function, how they get from one place to the next, you're going to have a challenge understanding insulin and glucagon, those hormones that are produced with patients that have diabetes. All right, so what is the endocrine system? What are its functions? Well, in the book, if you review Chapter 19, which you were supposed to, you'll see that we have numerous different locations throughout the body that are part of our endocrine system. And really the endocrine system affects every probably cell in our body, okay? So the endocrine system is composed of glands. Like I said, they're throughout the body, and they release messengers. Those are messengers, are the actual hormones themselves. So when we were talking about the RAS system, the renin-angiotensin-aldosterone system, aldosterone is released, right? That's a hormone, right? That's released to help regulate blood pressure, sodium and water retention, okay? Well, when we're talking about diabetes, the hormones that are released primarily that we're worried about are insulin and glucagon, those two hormones that are secreted from the pancreas. But think about it, the endocrine system, the nervous system, our immune system, they all work together. They all work concisely together to regulate both our internal and our external environment. And we really need to maintain our internal environment and what we know as homeostasis. The book goes over 5 different functions of the endocrine system, but we're really worried about or concerned right now at this point, since we're talking about diabetes, is really the maintenance of the internal environment. Okay, and then adapting to emergencies and the demands on the body. And you think of that with the fight and flight, sympathetic nervous system. And you say, wait, well, we're talking about epinephrine and norepinephrine and cortisol. Well, being secreted, those glucocorticoids. Remember, those impact glucose regulation as well, right? It increases the release of glucagon to take glucose out of storage so our body has more for ATP and for energy. Here's our endocrine system. The one we're worried about, that we are talking about right now, is the pancreas. We've already talked about the adrenal gland. We've already talked about HPA system. So we're focused on the pancreas right now, and specifically those islets of Langerhans, which we'll look at. But hormones only they convey regulation information between cells and organs, right? They're integrated with our nervous system, like I said, the neural system, to maintain communication and control. And there's 3 different types. We have autocrine, paracrine, and then our endocrine. So endocrine cells are remotely located, okay? Paracrine, the cells are located between each other. And then autocrine, it's communication within the cell itself. What are our characteristics of our hormones? Well, they operate within a feedback system. We think about negative and positive. Those are the ones we see the most, and we'll go over those in the next 2 slides. So they operate within a feedback system. They have rates and rhythms of secretion, and there's lots of different rates or rhythms. They can be diurnal, pulsatile, cyclical. They can be related to like ovulation. I can't remember what I was going to say. I'm sorry. But they can also be related to substances, right, or substrates. Those calcium is a big one, sodium and potassium, as well as the hormone itself. So the rates and rhythms of secretion, when we think about it, are really dependent upon, number one, the negative and positive feedback loop, and then those substrates, the amount of circulated substrates in the body, whether it's the hormone itself or some of those electrolytes. They only affect the target cells that have their receptors. So when insulin is secreted, it's only going to affect the target cells or plasma cells that actually have the receptor for insulin on it. It's the only way it can actually get into the cell to function and work. Whereas, and we'll talk about receptor upregulation and downregulation, which has to deal with those receptors too, okay? But then we have steroid hormones and peptide hormones. The ones we're talking about mostly are peptide hormones, polypeptides, insulin, and glucagon. There's a list in your book on the chapter in 19 that shows the list of all the hormones in the body and whether they're steroid hormones or polypeptide or peptide hormones. And what does that mean to you? Well, one is able to cross the cell membrane on its own without a messenger, without a carrier, and those are the steroid hormones. Whereas the peptide hormones, they're water soluble, and they require a messenger, a first and second messenger. So steroid hormones, where are they excreted? They're excreted by the kidneys and broken down by the liver. Whereas our peptide hormones, they're broken down by enzymes. They are eliminated in feces or urine. Okay, we'll get more into that too. So how are they regulated? Those hormones that we're worried about, and how are they released? Well, first of all, if they're released normally, they're released when either the hormone level is too low or too high. Their secretion stops, okay? But they are released typically due to an altered cellular environment to maintain the level of the hormone, or the substrate too, to maintain it at a therapeutic level is the best way to describe it. So there's chemical factors, and there's endocrine factors, and there's neural factors that affect this. So what's a chemical factor? What's an example of it? Well, a chemical factor can be your blood glucose or your calcium levels, right? If your blood glucose levels are low or too high. So insulin secreted by the chemical stimulation of increased plasma glucose levels. As we get into insulin, you know insulin is secreted when we have high blood glucose levels, whereas glucagon is secreted when we have low blood glucose levels. This is plasma levels, correct? So those are chemical. Endocrine factors. So a hormone from one endocrine gland controls another gland. So think about cortisol from the adrenal cortex. It's an endocrine factor that regulates and stimulates also insulin secretion. So I'm trying to tie it all back to insulin and glucagon. We do know, if you look back at HPA, hypothalamic pituitary adrenal glands, one must be in effect to make the other one get released to make the third one. So it's like a tertiary effect. But I want to tie it back to insulin. And then there's neurocontrol. So insulin itself is secreted by chemical stimulation of increased plasma glucose levels. So that's neural, to direct stimulation of insulin secreting cells of the pancreas by the autonomic nervous system. So we never get away from our sympathetic, autonomic, and parasympathetic nervous systems. You must understand those and how to differentiate them. Now, I told you we'd go into feedback systems. I highlight it. It's important to know, okay? They have negative and positive. All hormones do. So it's trying to figure out what that means. Well, a positive feedback occurs, and I have the definition on there, is when a neural, chemical, or those endocrine responses increase the synthesis and secretion of the hormone. So what's an example of that? High blood glucose, right? It's going to increase the release of the secretion of that hormone. So it occurs in response. Increases the synthesis and secretion of a hormone in response to something, whether it's high blood glucose or if it's another hormone. The negative feedback, think about it, the stimulus decreases the synthesis and secretion of a hormone. So negative meaning it's sort of stopping it and slowing it down. When you become hypoglycemic, or when your blood glucose is within therapeutic range, your pancreas is going to stop secreting insulin. It will pause. Positive and negative. So how are hormones transported? All right. So hormones are released into the bloodstream, directly into the circulation, right? And they are able to float around, and they do not affect other plasma cells or any other cells unless they have the receptor on there. And the receptors have the affinity, a high affinity to the hormone. Okay. So that when I come back to peptide and lipid soluble hormones. So peptide hormones, like I said, are water soluble. So they circulate free and unbound to anything else. So insulin is an example of this. Glucagon is an example of a water-soluble, but it also has a short half-life, so it must be utilized. It lasts like 3 to 5 minutes before it's catabolized by an enzyme, depending on which hormone it is. It has a specific enzyme that breaks it down, and then it's excreted in the feces and the urine, correct? So those peptide hormones are water-soluble, and this comes into play further on when we look at how they cross the membrane, okay, the cell membrane. Whereas lipid-soluble hormones, cortisol is an example, which we don't get into a lot with diabetes, but understand that cortisol does cause the net effect of an increased blood glucose, because it stimulates glucagon to be released and take glucose out of cells and break it down. The glycogen, that is. The glycogen, so to be broken down back into glucose and utilized. But it's transported, right, bound to water-soluble carrier or a protein that carries it, a transport protein. And it can remain in the blood longer, okay? It's not free-floating around there without any, in theory, protection. So only free hormones not bound to a protein can signal a target cell, okay? And there's always an equilibrium, okay? The concentration of those free and bound. It's sort of like osmosis and diffusion. And a change in the concentration of bound proteins affects our free hormone levels in the blood. So when you have a change in the concentration of a bound protein, it affects the hormone levels in the blood. Upregulation and downregulation. This is different than positive and negative. Feedbacks are based off the hormone levels and the need, correct? And what their mechanism of action is responsible for. Upregulation and downregulation are more related to the receptors that are on that cell membrane to capture that hormone. It's that sensitivity of the target cell to the hormone. There are a total number of receptors per cell. It can also be the affinity. It's like a magnet. If it has a high affinity, how well does it draw to it, to the receptors of the hormone? The more receptors or increased affinity of those receptors, like the magnet, the more sensitive the cell is to stimulate to the effects of the hormone. Okay? So what does this mean? So with upregulation and downregulation, your best bet is to really draw this out. But on the next slide, I have a picture of it. But upregulation, when you have a decreased concentration of hormone for, let's say, insulin, okay, floating around in your bloodstream, your cell will increase the affinity of receptors per cell. It will increase the number of them. So it's allowed to attract even more of what's floating around in the body. But with downregulation, if you have an increased or high concentration of the hormone floating around in the body, let's say insulin, floating around in high amounts, and your cells don't really need it, it's going to decrease the number or the affinity of the receptors for that cell. So what is it again? It's really the sensitivity of the target cell to a hormone. It's related to the total number of receptors per cell, and the cell can increase receptors or decrease receptors based off the amount of hormone floating around in the bloodstream. The more receptors or the higher the affinity, like a magnet, the more sensitive, once again, the cell is to the effects of that hormone, how they actually work. So affinity is what? It's really how a hormone binds to its receptors. How avidly, how much it's going to, how likely is it going to be, right? Or how the chemical forces that cause this substance to bind to the receptors, affinity. Once again, low concentrations of hormone floating around in the bloodstream increase the number or affinity of receptors per the cell, upregulation. And then high concentrations are just the opposite. They decrease the number of receptors or the affinity of the receptors. It's downregulation. So the feedback loops, positive and negative, are really going back to the hormone-producing body itself, whether it's the pancreas, secreting insulin, If you have too much, your blood glucose level is low, the insulin is going to be decreased. Whereas if your blood glucose level is high, your body is going to, the pancreas is going to make more insulin to be secreted. Upregulation, downregulation, positive feedback, and negative feedback. So this is straight from your book, the picture. It just shows upregulation and downregulation. Once again, what's their job, right, with these? It's really to recognize and bind with the affinity to their hormone, right? With high affinity, and to initiate a signal for intracellular effectors. So glucose moves into the cells with receptors along with insulin. Okay, why is glucose moving into the cells? Well, to be utilized for energy, for ATP, right? But it can't get in there alone. Insulin pushes it in there. Insulin's the key. So insulin opens the membranes and allows the blood glucose to move and generate energy. Insulin also binds to the receptors, right, which changes the membrane permeability to glucose. So when insulin binds, the key opens up. It allows the glucose to come through. In a nutshell. As you can see here, upregulation. There's not a lot of hormone floating around in the bloodstream. So the cell has more hormone receptors at the target cell to capture more. And downregulation is the opposite. Too much is floating. So with downregulation, another way to think of it, as I try and explain it, it really allows the cell to become less reactive to the excessive hormone levels that might be floating around in the body. Okay. What's this mean? If you look at the whole thing about the endocrine gland, hormone, target tissue, and receptors, we know what an endocrine gland is, right? It's a group of cells or tissue, or it's an organ that produces and secretes hormones directly into the bloodstream, right? And then what is a hormone? It's a chemical or substrate or a messenger that stimulates cellular action in the target cell. It only affects its own target tissue, its only target cells, that is, into the target tissue, but it only affects its own cells, correct? That it has receptors to. That target tissue is the specific tissue that the hormone can influence. And then receptors, they're sites on the target cell, right? Their location with where that hormone gets actually attached. So they can recognize and bind with high affinity to the hormone. And then they initiate intracellular effectors. So the hormones travel through the bloodstream, but they can only exert their actions on what? It's the target tissues themselves. And those that have the receptors. So the target tissues have receptors that are specific to the hormone. Okay, types of hormones. This is just a repeat. This is from your book. Fat-soluble versus water-soluble. What do you see the difference in here? Like I explained to you, water-soluble requires a second messenger to cross the plasma membrane, to get through there. So the fat-soluble don't. They go in there. They're able to pass through. And then they have their intracellular receptor in here, and they, cause changes to the effector cells within the inside of the cell. So here's your plasma membrane, right, outside the cell, whatever cell it is. The water-soluble hormone, that peptide, remember peptides or polypeptides are water-soluble. This is your first messenger, and it gets it to the second messenger. And then I'll explain a little bit better in the next slide that you have protein kinase A or C, and then the cellular response that occurs. So receptors can be located on the plasma membrane with water-soluble, or intracellular, inside that compartment of the cell. That's why fat-solubles hormones don't impact the plasma membrane. They go directly inside the target cell. The difference in the two. So water-soluble, protein hormones and catecholamines. Okay, what are your catecholamines? You must understand which ones are catecholamines. They circulate free and unbound, but remember they have a really short half-life or acting response, 3 to 5 minutes before they're catabolized. They do have a high molecular weight, which is why they cannot get passed through without that primary messenger and secondary messenger. They bind to the surface receptors. They initiate first and second messengers. Whereas lipid-soluble, they're steroid hormones, right? They're primarily bound circulating to a carrier in the bloodstream. They're small, and they have a long-lasting effect or response. They do not get broken down easily. And they diffuse freely across the plasma membrane and nuclear membranes, and they bind with what's called systolic or nuclear receptors. So they have their action within inside the cell. Once again, examples of water-soluble, insulin and glucagon are your water-solubles. They're proteins, they're peptide hormones, right? And whereas the lipid-solubles, cortisol is one. And then your adrenal androgens are one. Think of steroids. They can signal the target cell. They can go right through the plasma membrane. We're more concerned with water-soluble, so I eliminated the fat-soluble slide because water-soluble is what we're talking about with insulin and glucagon, the two big ones that we have that are related to diabetes, insulin sensitivity, insulin resistance, and everything else. So as you can see, once again, there's that protein hormone. There's the first messenger. It's the first messenger, right? This is its receptor, okay? So the hormone is the first messenger. So it's delivering the message via our bloodstream to the membrane receptor, right? It only will respond to its own at the target cell, like a key. Okay? Oh, sorry, guys. I went too fast. That second messenger with water-soluble hormones causes the cell to respond and perform its specialized function. Okay? It's doing all this stuff with the enzymes, cAMP, which is the second messenger. So ATP causes cAMP, which causes and activates other enzymes. And then it regulates the cellular activity. I'll go into it in the next slide. Okay? But so like insulin's the first messenger, correct? Insulin right here. Let's say that's insulin. And it binds to the surface receptor. It activates the second messenger. It activates the tyrosine kinase family specifically, right? And they regulate a wide range of intracellular processes, right? And it helps contribute to cellular metabolism and growth. Okay, what's it allowing to get across the cell membrane? The glucose. Okay, so let's get back specifically to the hormones we're concerned about with diabetes. The organ that produces these is the pancreas. And we have alpha. You must know the difference in these: alpha, beta, delta, and F cells that are all in the islet of Langerhans. Okay? It is an endocrine and exocrine gland. We're primarily concerned, well, we'll go over both because the exocrine gland portion of it has a purpose as well within the stomach and the intestine and slowing down motility and everything else, or increasing additional glucagon secretion, put it that way. So endocrine gland means something that's produced within the cell itself. Exocrine gland means it's produced outside it, right? The endocrine gland, it's producing the hormones, and the exocrine is producing digestive enzymes. The pancreas is, okay? These hormones are important because they regulate carbohydrate, fat, and protein metabolism. So once again, this is a snippet, as you can see, right here, and this is blown up. There's your alpha cells. They secrete glucagon. Your beta cells, they secrete both insulin and amylin. Your delta cells secrete somatostatin, and gastrin. Right? And then the F cells, it's a pancreatic polypeptide. We won't talk about that one as much. So the beta cells, once again, produce what? Insulin and amylin. We'll go over those first, even though alpha seems to be, in theory, more important because it's alpha, but it's not. They're both important. But insulin, it's what we talk about, right? So insulin's actually synthesized from another hormone called proinsulin, all right? Insulin's produced from a precursor, proinsulin. And why is it important? Because when it breaks down and cleaves off, you'll understand why we sometimes talk about C-peptide levels and why we measure them. But so insulin's produced from the precursor proinsulin. It's formed from a larger precursor molecule called preproinsulin. Do you need to remember that for the exam? I would understand the next portion of it more. But understand it is produced from something else. Okay, proinsulin, here's what's important, is composed of A and B peptide. And then it's connected by a C-peptide. The C-peptide is the one that's cleaved by the enzymes, right? Which leaves the bound A and B peptides as the insulin molecule. So proinsulin is composed of A and B peptides. Then it gets connected by a C-peptide. That C-peptide is cleaved, broken off by an enzyme, which leaves the bound A and B peptides of the insulin molecule. Why is it important? The C-peptide level is the one that can be measured in the blood, and it's really an indirect measurement of serum insulin synthesis. Okay? So the C-peptide level can be measured in the blood, and it's used as an indirect measurement, once again, of serum insulin synthesis. So insulin is synthesized from the proinsulin, which is really a larger molecule called preproinsulin. What makes it secrete elevated? It's promoted by increased blood glucose levels. Remember your positive and negative feedback. It's also stimulated by the parasympathetic nervous system. So before meals, and some amino acids and some GI hormones. So insulin is secreted by the parasympathetic nervous system before meals because it's anticipating an elevated blood glucose level, some amino acids, and then some of our GI hormones for the same reason, anticipation of nutrition or oral intake. It really is that key. Remember the locking key mechanism that facilitates the rate of glucose uptake into the cells. Okay, and it's an anabolic hormone. Synthesis of proteins, lipids, and nucleic acids. So insulin sensitivity of the receptor, that's that receptor that's on the cell membrane. So unfortunately, our sensitivity to insulin is affected by our age, our weight, abdominal fat, and our physical activity, or you could say physical inactivity. So in advancing age, you have decreased insulin sensitivity. Increased weight, decrease. Increased abdominal fat, same thing, and inactivity is the biggest thing. Physical activity improves insulin sensitivity. Losing weight improves insulin sensitivity. Okay, and it's important because it allows the glucose to not be floating around in the body. It allows it to be stored in the liver or utilized. Insulin resistance, which means you're resistant to the insulin. Those receptors are resistant to the insulin. You still are making insulin, right? If you measured your C-peptide levels, you're still creating insulin, the body is, from the pancreatic beta cells, but it's not as effective. It's not the cell receptors, the regulation of them are not, the affinity to them are not as, they don't have a high affinity. Hypertension, heart disease, and obviously type 2 diabetes. Because in type 2 diabetes, we become insulin resistant. The insulin doesn't work as well that's floating around in the body because it's been produced over and over and over because of the chronic high blood sugar levels, blood glucose levels. And then adipocytes, they release hormones and cytokines, as you can see, as we were talking about earlier, that are altered in obesity, and they have an impact on insulin sensitivity once again. Weight loss, like I said, and exercise improve insulin sensitivity. The more sensitive your body is to the insulin, the more glucose that gets taken out of the bloodstream and stored. Okay? And why does our body make insulin? Well, we've said it numerous times, but it's to promote glucose uptake. So primarily in the liver, the muscle, and the adipose tissues. So fat, right? Liver, muscle, and adipose tissues. Insulin also increases the synthesis of proteins, carbs, lipids, and nucleic acids. So it says, I put down there insulin's net effect. Its goal is to stimulate protein and fat synthesis and decrease the blood glucose level. What you must understand and remember and never forget, the brain, red blood cells, kidney, and the lens of the eye, they don't require insulin for glucose transport. Okay? But the brain relies on glucose. Insulin, if we give insulin, it's not going to get glucose into the brain. The brain doesn't make its own glucose. The brain does not store its own glucose. Okay? That's what's so important. It also facilitates the transportation of potassium. This will come into play when we talk about diabetic ketoacidosis, or when we talk next semester when you talk about Addison's disease. So think about it. Insulin, if we give intravenous insulin, IV insulin, or subcutaneous insulin as an injection, it moves potassium back into the cell, as well as phosphate and magnesium. So if you have a patient that has a really high potassium, like let's say 6.2, you might be giving them insulin injections. You say, well, with their blood glucose level, they're not diabetic. What might you have to give them too? Glucose, intravenously or orally. Typically, it's going to be intravenous because it's a tight correlation between the two. So insulin really promotes glucose uptake in the liver, muscle, and adipose tissue, right? It helps with the synthesis of proteins, carbs, lipids, and nucleic acids. Right? We really want it to stimulate protein and fat synthesis and to decrease blood glucose levels. And you're thinking, well, where's the glucose going? Well, it's either being utilized and uptake into the cells for energy, ATP production, or it's being stored in the liver, the muscles, and unfortunately the adipose tissue if there's too much glucose. Okay? But over time, if you have elevated blood glucose levels, chronic ones, which we'll talk about on Thursday, your body produces more and more insulin to try and counteract the elevated level, and the body becomes less sensitive to it. And that's what we were talking about in the previous slide. Great picture. It looks scary, but it's just what I was talking about. Insulin's action on cells. So here's your insulin, right here. There's your receptor. Doesn't look the same, but it is, right? What's going on here? There's that tyrinase, kinase that was being made, right? Insulin receptors, substrates 1 through 4. GLUT is the one that's the most important one. And we'll talk about that in a second. So the insulin receptors cause glucose transport, fatty acid synthesis, as we were talking about, protein synthesis, glycogen synthesis, cell growth and survival, and an amino acid electrolyte transport. Right here are your electrolytes being transported into the cell, potassium, mag, phos. Amino acids being brought into the cell for protein synthesis. And when your insulin's attached, remember, it's the primary messenger. The secondary messenger within the cell, it's the lock and key mechanism that allows glucose to be transported across the plasma membrane by this receptor right here, GLUT, otherwise known as glucose uptake transporter. It's GLUT, whatever you want to call it. Glucose uptake transporter. It transports the glucose. It's a transport protein. So insulin promotes cellular glucose uptake through GLUT4. Insulin's action on the cells once again. So the binding of insulin to its receptor causes a phosphorylation, an autophosphorylation of the receptor, okay? It acts as tyrosine kinase, right? That I can never say these words. Phosphorylates insulin receptors, substrates 1 through 4, okay? That's a lot of words. I can't say them. I don't expect you to say them, okay? But what is more important to understand is that insulin receptor substrates 1 through 4 allow glucose transport to become the GLUT4 to become the vesicle that transports glucose. All right. So, what else do I need you to know about this? So, glucose uptake transporter is recruited into the plasma membrane, right up here, where it facilitates the movement of glucose into the cell. It's that lock and key mechanism. Where else does it do? It facilitates glucose into the cell, and then also insulin facilitates the transport of the amino acids, potassium, mag, and phos, into the cell. And remember, potassium always has a higher concentration intracellularly than extracellularly. So insulin, let's look at this slide. I don't know if it's going to work. Here's your pancreas, right? Here's glucose floating around in the blood. So too much glucose is floating around in the blood. Just floating. You ate too many carbs. So it increases the pancreas beta cells to produce insulin. So insulin does what? Goes onto the receptors, and it takes the glucose out. There's your glucose channels, and there's your insulin receptors, and it stores it into skeletal muscle, fat, primarily in the liver. When the liver can no longer store glucose as glycogen, it goes into muscles, storage, primarily adipose tissue as storage, and skeletal muscle. There's your negative feedback loop, this side, right? Once the glucose levels are down, it tells the pancreas to stop producing the insulin, because now you don't have very many. It used all these, see, 1, 2, 3, 4, 5. Now you have one left. You had one went there, one went there, one went there, and I don't know where the other guy went. He's floating around somewhere still in the body. So our beta cells, amylin, the other one produced by the beta cells. The first one is insulin. And you don't hear a lot about amylin. It sort of gets, it's sort of forgotten. It's like, it's a peptide hormone. It's also secreted with insulin. But what does it do that's important? It delays gastric emptying. So you have a large meal, and your body is anticipating glucose. Remember, it gets secreted in anticipation of large meals, but amylin is secreted because it anticipates too much sugar to be absorbed into the bloodstream, glucose. So it just delays gastric emptying. It also suppresses glucagon secretion after meals, which we talk about glucagon next. Glucagon makes more glucose readily available. It makes you feel full. Satiety effect. It makes you feel like, I'm not really hungry anymore. Amylin does. And this is when it's working perfectly. This is when it's working in the right environment, and there's nothing wrong. And it works to prevent hyperglycemia, the two of them hand in hand. So insulin and amylin are produced together. They're co-secreted, but they have different purposes. Then we get into the alpha cells. Glucagon's the other big one that we talk about. Glucagon and somatostatin from the delta cells. But glucagon's from the alpha cells. What's it mean to be an antagonist? It has the opposite effect to insulin. Insulin brings glucose out of the bloodstream, and either for utilization and uptake, right, using GLUT, glucose uptake transporter, or stores it in the liver as glycogen or stores it in adipose tissue or muscle. Okay? Glucagon does the opposite. Its feedback loop is stimulated by low blood glucose levels. So less than 70. Our normal range is 70 to, I think, 110. But we'll get into that. And it's also stimulated by the sympathetic nervous system, sympathetic stimulation. So it works primarily in the liver because that's where the majority of our glucose is stored as glucagon. When our insulin has taken it out of the bloodstream and stored it after it's all been utilized as necessary, and we have our therapeutic level of the 70-ish to 110, once the liver is maxed out of storage, it goes into the fat cells and everywhere else to break down. That's where you get breakdown of protein and fats and carbohydrates, amino acids, and we have lactic acid built up. But it works primarily in the liver, and it increases our blood glucose concentration. It stimulates the terms you must memorize: glycogenolysis and gluconeogenesis. Okay. It inhibits high blood glucose levels, and I'll get more into it. So it's an antagonist to insulin. It's stimulated by low blood glucose levels. It's also stimulated by sympathetic stimulation. What does that mean to you? Sympathetic nervous system, the fight or flight. It's going to pull stored inert glucose out, stored glycogen out of the cells, break it down into glucose for uptake and utilization, for muscle, for energy, for fight or flight, for running. Works primarily in the liver because that's where the majority of our glucose is stored as glycogen. Somatostatin, it's produced in response to food intake, okay? And it's essential in carbohydrates, fat, which I misspelled, and protein metabolism. So it regulates the alpha cell and beta cell function within the islets of Langerhans, I guess you could say, as they are, by inhibiting secretion of insulin, glucagon, and pancreatic peptide. So it's produced in response to food. It also regulates alpha and beta cell functioning. And it's essential in carbohydrate, fat, and protein metabolism. The glycos, the ones you have to know. I will unhighlight this. I don't know why it got highlighted. Okay. What's happening in the liver? Glycogenesis. Right? Insulin promotes the production and storage of glycogen in the liver. Glycogenesis. Glycogenolysis. Glycogen breakdown into glucose in the liver. Glucagon does this. Beta and alpha cells. And outside the liver, we have gluconeogenesis. It's the conversion of proteins to glucose. And ketogenesis, the conversions of fats to acids. Think of the keto diet. Even though it's probably not a good explanation, but we have a lot of lactic acid. We have a lot of buildup. You have to know these terms. Olysis, enesis, and enesis. Okay? Those four. So what's our insulin do and not do? Well, in the liver, that's our liver, insulin, it promotes glycogenesis, which is the production and storage of glycogen. Inhibits glycogenolysis, which is glycogen breaking back down into glucose and being pushed back into the bloodstream. And it increases protein and fat synthesis. Right? I'm not sure what I meant by let's learn some of the conversions, but it also inhibits ketogenesis. Oh, the conversion of fats to acids, the breakdown of fats into acids, and it inhibits insulin, gluconeogenesis, the conversion of proteins to glucose. Okay. When you burn proteins in your urine, when you burn proteins, you have ketones in your urine. It's a spillover effect. What am I doing? I don't know. There we go. So let's go back to glucagon again. So what does it do? Once again, glucagon is a counter-regulatory hormone, right? It's the antagonist to insulin. So glucagon increases your blood glucose. It's the opposite of insulin. When you need more energy and your blood glucose levels are low, glucagon is going to be secreted based off that feedback loop, right? And then glucagon causes glucose to be released from the liver, also known as what? Glycogenolysis. It's breaking down of glycogen back into glucose from its storage unit, the liver. And it also converts amino acids into glucose. So when we're depleted of liver glucose stores, let's say you're in starvation mode, you've just run a double marathon. We need fuel, right? That's when we have a breakdown of fat and proteins, lipolysis and proteinolysis. And that's not good. Well, I mean, some people, if you're obese and overweight, you want to break down your fat, right? And you will do that based off, controlling your food and portion intake, because you do not want to overstore glucose because it gets stored into the fat cells. But that improves insulin sensitivity, okay? But within starvation mode, especially when we're breaking down our proteins and our muscles, we have proteinolysis, or we end up with ketones. And why is glucose so important? Besides the fact that that's how we survive, ATP, we need glucose for energy. But once again, why does it need to be maintained at such a therapeutic level and not drop too much? Well, our brain cannot produce or store glucose. So its regulation, its requirement, the brain requires glucose in the bloodstream. So we never have zero glucose in the bloodstream unless you're in a coma, or you're dead, or you've completely starved yourself and you will die, right, without any glucose. Or you're seizing. Typically when a patient's seizing, their seizure activity will stop when the brain runs out of glucose, because it runs out of energy. Unless you're in a, we used to call them grand mal, but they're not called grand mal anymore. So, but anyway, seizure that's going to last longer than 10 minutes, your patient's likely going to die. I mean, they have a greater risk of dying. You've got to break that seizure because they run out of glucose stores, okay? Other organs use glucose and fatty acids to generate energy as well, okay? As we know, because that's why they are uptaked into cells for energy. Okay, how's it stored once again? As glycogen in the liver and skeletal muscles, okay? When more glucose is present in the liver, it can be used. It's packed up. There's too much glycogen storage in there. It can be converted to free fatty acids, such as triglycerides in fat cells. And that's why elevated triglycerides are part of our metabolic syndrome. Precursors to diabetes, precursors to hypertension, coronary artery disease, stroke. When we have prolonged fasting or illnesses, meaning we're not taking in enough food, carbohydrates, or anything else, our proteins are then broken down. And some of the amino acids are then converted into glucose. So, first of all, glucose is stored as a glycogen. And where is it stored? Liver and skeletal muscles, and it can be also used for energy. It can also have excess glucose converted into free fatty acids, such as triglycerides. And then the opposite is during prolonged fasting or illnesses. It's broken down. When there's too much glucose, I just went over this, causes excess glucose to be converted into free fatty acids, such as triglycerides, and these are deposited in our fat cells. What starts and stops insulin secretion? Okay, what is this known as? your feedback loops, okay? Insulin secretion is increased. It's driven by an increase in serum blood glucose levels. It's stimulated by the parasympathetic nervous system before we eat meals, okay? Also, secretion is decreased with low blood glucose levels. High levels of insulin, the negative feedback loop, or the sympathetic stimulation of the beta cells. What are your beta cells? Once again, glycogenolysis and gluconeogenesis. Apparently you must need to know these. And then another quick picture as we go into diabetes, and then I'll stop there just to get you guys ready for next week. It's just a picture. It depicts what's going on with the beta cells. So diabetes, we have type 1 and type 2. And type 1 is typically diagnosed around the ages of 12 to 14. It doesn't have to be, but it's typically an autoimmune disorder. And macrophages attack our beta cells. And if you do not have beta cells, you will no longer have insulin produced. And you will have high levels of glucose. It happens slowly over time, so it's not instant. So that's why you do not have such a high blood glucose level, but you start having symptomatology, which we'll get into. Okay. And what happens? What causes the breakdown or the attack of the beta cells? Typically, it's genetics. You have a family history of it. It can be geography, where you're located, age. It could be from a virus, lots of different things. Okay. And that's it.